Welcome everybody. Today we have this. We're running a webinar here in parallel with this session. Okay, welcome everybody. Today we have a seminar here together with the Ekkono solutions. The main subject is in is AI, the future of IoT. Let's see. Okay, there's something to present. Okay. My name is Martin Nordström. I'm account manager from Realtime Embedded. I'll introduce a little bit short about Realtime Embedded first. The company was founded year 2000 here in Stockholm, in Sweden. We are today around 37 people, and the company actually was founded by some of the consultants, and actually today also some of the consultants are owning the company. Our focus areas, we are working with the product development, such as a lot of different kind of in-house products. For example, today we have a lot of in-house products related to field service solutions and predictive maintenance. And you can say also in total we have some kind of product office set up when it comes to different kind of functions and projects. And we also offer consultancy services on site. And we also offer education. We are partnered, for example, with ARM. So we offer a lot of education together with them. And we also have a lot of educations when it comes to embedded Linux and also FPGA and also GitHub, or control version handling. And what maybe make us a little bit more unique as a company, I think that we do research. We are actually involved in this RTE or Excel. Maybe you heard about this European research project, research organization. It's the EU projects research. And actually today we are involved in one big project called Scott, and it's about to build up independent cloud platforms. So it's one big project we are involved in just now. When it comes to what Internet of Things, for us as a company, we have seen the last years very important actually to have some kind of thing, just not to make things. I think you maybe have seen this before. So, for example, that is some kind of strategy established in the company before you start with some kind of project, that you have a vision in the company, established in the whole company, for example. When it comes to these field service solutions, for example, it's quite common that you need to start very often in the aftermarket department in the company. And then it's quite important that the whole vision of this idea is implemented with the R&D and everything in the whole organization, so it becomes much more better. And then, here's a little bit what we think you need to catalyze your vision or your idea. For example, we can see from our customers, we have experience that maybe you need to start with some kind of ideation phase or something if you have some kind of field service project. And after that, implement some kind of workshop where you look on the business model and do some kind of transformation from your old business model on the aftermarket department. And then maybe later you can start with some small pilot trial, and after that you can evaluate a little bit more and see how it works. So actually think big, but start smart. Start with a smaller system. Here's one of our reference cases, De Laval. Maybe you're aware of the company. I don't know. Is no one?
Yeah, for sure, of course.
Yes. De Laval actually is a company who deliver milk machine solutions for different farms in the dairy industry. And here we have done a typical field service integration. We have actually integrate from the sensor level. You can see here, for example, you have the gateway here. And we have different kind of milking points here, for example, connected to a robot. And we have done the integration from the sensor level up to the gateway. And here we also have done a lot of security analytics also, and also a lot of testing and integration. And So this is a typical case actually, and this typical killer app. For example, this, I mean, the milking farms, they are very often located in very isolated places. So this is this typical case when you really find the big benefits. You know, I mean, these farms, they are located very isolated. So this is this typical killer app when it comes to field service solutions. So Harry. North Star battery is another customer case. Here you also have this aspect that the system very often is isolated. When it comes to this system, it's more about some kind of UPS solution, that you have the batteries on the UPS close to the base station, maybe can be isolated. And then you have this also process monitoring, that you can do a lot of remote process control. And in this case, we have done integration also from a gateway to the sensor level, from the sensor level up to the gateway. And there's two aspects in this. Actually, one of the cases that you have this system located in the logistics center where you have the batteries stored. And there is very important that you have a very good condition on the batteries. So if you can have the optimized conditions on the batteries, you can save at least 30% of the money. So this is quite a big revolution in this industry, that you can, especially for the telecom industries, that have a lot of costs for batteries. And this is all you can say. For example, this is the typical case how you have a simple product that suddenly become a smart product from battery. Realtime Embedded, here you can see a little bit about our services. For example, we do analysis of our systems and products. We can also help you with the business model transformation. We have partners for that. We work with system architectures, security data analytics, product development, deployment strategy. Here you have a spectrum of our customers. I think some of you are here today. So it's in a lot of different kind of technical domains in different diversities. So I think I would say, think big, think smart. Okay, I will hand off to our partner, Rikard from Ekkono.
Okay, let's see if we can. So, hello everyone, and hello everyone in the webinar. I hope you can hear us good. My name is Rikard König, and I'm the Chief Data Scientist of Ekkono Solutions. I'm also a senior lecturer at the University of Borås in Sweden. I'm actually a researcher. I've been researching for the last 12-13 years within machine learning. I've been doing research projects with Scania, trying to predict fuel consumption in the trucks, with ICA to predict campaign sales. I've even been analyzing the golf swing using a radar to see how you can improve your golf swing. And I'm the member of a research group in Borås called Computer Science Lab at Borås, CS Labs, consisting of 10 researchers focusing on machine learning and high performance computing. Today, I will give a talk about AI, artificial intelligence, and the future of IoT, or that AI will be the future of IoT, I hope. So let's start with that. The agenda, like that was in the invitation as well, is that I will start to speak about the potential and challenges of IoT. Then I will explain a bit more about AI and more specifically machine learning and how it's applied to IoT and how it's actually working. And I will give you some typical use cases of what you can do with machine learning and IoT in the end here. And I will start big, in the big picture and the big, not the big details, without the details. And then we'll come down to more technical aspects in the end. So I hope everyone will get something from it. If you think the beginning is too simple, you will get more food for thought in the end. So let's start then with IoT potential and challenges. So we all know Internet of Things as the network of physical devices, which enables all devices to communicate and exchange data with each other. This is a word cloud about words that are connected, related to Internet of Things when you do a search. And what's interesting with this slide is that if you look closer, you can see that lately it's been popping up all this smartness, smart machines, smart big data and statistics. But we realize that it's not enough just connecting things. We can do so much more if we actually analyze and do something smart with the data. That's where the real power comes from. So what's the potential economic impact of IoT? Well, McKinsey and company estimated to $3.9 to $11 trillion per year, the year 2025. That is, I don't know how many zeros. It's a lot of money, no? And it's interesting to see as well that it's actually not consumer products that is getting the most benefit or have the largest potential, but it's rather business application and business-to-business applications where the largest values are. This data comes from a report called McKinsey Unlocking the Potential of Internet of Things. Look it up on the internet and you will get a detailed description of how they come to these numbers and a lot of interesting facts into the potential of IoT that I won't be able to go into today. But when they speak about factories, they're speaking about predictive maintenance and machine optimization specifically. There's the greatest potential there. When we speak about cities, it's healthcare, it's traffic planning, and keeping the city's maintenance running. Human, then it's monitoring and keeping and handling illness and keeping or enhancing the wellness of people. Retail, we're speaking about automatic point of sale stations and smarter customer relationship, such like that. Outside there it's smart logistics and navigation. And in work sites and vehicles, it's again predictive maintenance and control and increasing the security. Autonomous vehicles, of course, and so on. So there's a huge possible impact of IoT. And I guess that's why we have so many interested people here today. But how can it possibly be $10 trillion per year? What's the basis of that? Well, one thing that you need to keep in mind is that the IoT explosion, before it was the processor power and it's still going, following Moore's law, and now I guess it's the number of connected things. At the birth of IoT 2009 was about 6 billion of connected devices. And now we're up to 34.8, and it's predicted to be around 50 billion devices the year 2020. So when they look at the potential of the Internet of Things, they are calculating that this development will continue. And it's not sure that it will do that, of course. There are some enablers and challenges that they mention. What needs to happen for IoT to reach this potential and get this spread? Well, first we have the software and technology that needs to keep becoming cheaper and cheaper. The last 5 years, the typical sensors that you use in smartphones has dropped with between 70 and 30%. And they're calculating that this will continue. So the sensor will be becoming cheaper and cheaper, and then we can put it in more and more products. Interoperability, hard word maybe. All the IoT devices need to be able to speak with each other to be able to fulfill all this, the full potential. To be able to use it, you need to connect all the dots. And they say that without that, 40% of the potential benefits may be lost. So it's really good it's really important if you have an IoT system, or if you go into IoT, that you have a good plan from the beginning, or that you have a really good partner that can do the integration. Privacy and confidentiality. Well, if we're going to collect data from 50 billion devices, we won't have any privacy anymore. So of course we need to somehow handle all the thoughts and all the feelings around that, both for common people and among our organizations. So that won't be something that stops the growth of IoT. Security, of course, if we connect that many devices and sensors, there will be so many more places for potential breaches as well. So if we're going to send all that data to the cloud, there will be so many streams of data that can be attacked. So that also has to be managed in a good way. And then we have the intellectual property. Who owns the data? I mean, now with the new data laws in Europe, where a private person has the right to their own data, they has the right to be forgotten and all that. And this, so, I mean, we started to realize the worth of data, the worth of our own information. So we need to look at that, and what happens if one organization creates the sensor or have a sensor network, another one uses that sensor network, who is owning the data, and we need to be able to handle that in a good way. And then of course it's regulatory hurdles, like we need to have the laws and everything that's supporting it. And the typical example here is self-driving cars. Who is responsible if the car crashes? All those legal aspects need to be clarified for us to be able to start driving autonomous cars. One last, but definitely not least, challenges is that the data is not used. McKinsey states that on an offshore oil rig with 30,000 sensors, only 1% of the data is actually used for several reasons. And why is that? Well, first, 40% of the data, less than 40% of the data can be stored. So it's just, they don't have enough, they don't have a strategy for storing the data or what to do with it. So they're actually not storing the data, maybe just looking at it. And the infrastructure doesn't support sending the data to onshore or to the cloud. So only 1% of the data can be streamed. That's a huge problem to start with. And then you have the data management, that the data that is stored and recorded can't be accessed in real time. So you can only do ad hoc analysis and definitely just in retrospective. And we're usually limited to just a few metrics instead of all the machines connected to the network. And there are also rarely interfaces to deploy real-time analytics systems and models. And even in those cases when you have all these things in place, the people and processes are not using them in the best way. You always need to get the new technology into the organization. So even if they have support, they still follow manufacturer recommended service intervals, for example. So there's a lot of hurdles for IoT to reaching the full potential. And today we'll try to give you some kind of idea about how to solve some of them anyway. We won't have all the solutions today, of course, but we have at least one idea about how to go about things that we'll see. Like I said, McKinsey states that most of the data is not used. And the data that is used is only used for anomaly detection or control, real-time control, not for optimization and prediction, which provide the greatest value. And to do optimization and prediction, you usually need to have some AI. That's why we're going to speak about AI later here, because that's how you can get the greatest value from IoT. And IDC states in that line that in 2019, next year, 40% of all digital transformation initiative and 100% of all IoT initiative will be supported by AI capabilities. So people think that AI will be really important for IoT and the development and potential of IoT. Okay, that said, what is AI, artificial intelligence, and machine learning? That's the next part of this talk. Well, it's an old field, artificial intelligence. It's my favorite field. I think I started when I was 12, looking into this, how to beat the games, how were the computer games constructed. And a lot of the research today use computer games as a platform for developing and testing algorithms. So it's a lot of fun. But the simplest definition is that artificial intelligence is intelligence demonstrated by machines instead of humans. So some kind of intelligence. And you have many specialized subfields. You have logic reasoning, knowledge representation, planning, optimization, natural language processing, perceptron. I mean, if you think about AI, you think about a robot walking around, and then you can just guess all the things that the robot needs to be able to do. That's all part different fields of AI. What we will be speaking about today is machine learning. So it's one subfield of machine learning, of artificial intelligence. Often today, artificial intelligence is connected to voice recognition, speech recognition, and image recognition, which is deep learning. And deep learning is a subfield of machine learning. So what is machine learning? Well, it's the field that gives the computer the ability to learn from examples without being explicitly programmed. Okay, so we need to have examples of the things that we want to learn. And there are, again, 3 subfields of machine learning. We're going down the rabbit hole here, I guess. The first one is reinforcement learning. And that's where you have an agent interacting with an environment and needs to learn something about its environment. And if it does something good, it gets a reward. And if it makes it bad, it gets a punishment. Thereof, reinforcement learning. And most of the game AI that you see and use today have some part of reinforcement learning within them. You maybe read that Go was sold now, or not sold, is far from sold, but the best AI Go player today beats the best expert, and they thought that they'd never do that. And that's with a reinforcement learning agent that has learned to play Go against itself. So if it wins, it gets a reward. If it loses, it will get a punishment. And then it needs to explore all the possibilities. Unsupervised learning, then you look at the data and see which instances of the data, which examples are similar. It can be, for example, typical clustering. If you go to ICA today and shop, your data will be clustered and you will be categorized of which type of customer you are, so they can direct commercials for you, for example. But you can do that as well in other areas as well. Anomaly detection is also looking at the examples and see which examples are not typical. It's not normal. Of course, all the examples will be different, but some will stand out in a way that the others do. So the thing is here is that you don't have a faucet. You don't know the right answer. You can have many solutions, but no one can say it's, or at least it will be subjective. If it's correct or not. You can have different metrics saying if it's how good it is, but again, it's always subjective. And then what we will be speaking about today is supervised learning. Prediction, forecasting, and classification. That is, you have examples and you have the correct answer. So let's take a weather forecast. You can make a prediction and then you can learn afterwards if it was correct or not. Yeah? And if you save the data and the actual weather for a year, then you will have a knowledge base that you can learn from. And you'll have your examples and your target variable. You can do prediction, estimating the value of a house based on 100 other houses you've been seeing before. And you can do classification, saying that if the example will belong to one of two classes. Is this a machine that will fail in 10 minutes or be healthy in 10 minutes? There will be classification. And then as you see, you have deep learning here. It's a subfield of supervised learning based on artificial neural networks, which is a technique that was invented in the 80s, I think, and it's based on how our brain works. Right now, you just stack them with much more neurons, much more layers, and then you get a deep neural network that can do all this image recognition or something, everything like that. And we can do it now because we have more computer power. But we will be looking at classical machine learning. I won't be speaking about deep learning today, because there is not so many, well, I argue anyway, IoT cases where you have image recognition or voice recognition. It's more sensors measuring temperature, vibrations, pressure, flow, whatever. Yeah. So that will be the focus of this. I call it good old-fashioned machine learning. So what is it? Learning from examples. This is an example. Can you learn something from it? I can explain what it is to start with. Can anyone guess what this is?
Generator?
Yeah, almost. Well, it could be a generator. It's supposed to be a substation. Maybe I took the wrong picture on the internet. I actually don't know what it is. But the data that we see here comes from a substation delivering power to 7 houses. And the thick line here is the total power consumption, which should be read on the first axis here. And the other small lines are the individual houses' power consumption, which should be read on the second y-axis. So yeah, we start to complicate things, but it's just, the point is, we want to be able to learn this line from all the others. And we like to see it in this form, like a chart, because it gets so much simpler, doesn't it? You see straight away what can do it. A computer would, of course, like to see it like this. This is the same data. Can you see how much simpler it gets? Yeah. Well, we could at least have guessed something from this chart, but the computer will look at it this. And most machine learning algorithms is actually based on common sense. I teach machine learning and data mining in the University of Borås, and the first assignment that I give them is I give them a sheet like this, a little bit smaller, and I say predict these values, and write down how you reason. And every time they do it in 2 or 3 ways, and each of those 3 ways is actually machine learning algorithms. So if you would try to go about thinking about how to do it, you would use, I'm sure that you would use 1 or 2 machine learning algorithms. It's common sense, automated with the computer. And then you have the more fancy one like artificial neural networks that you need to understand the brain and stuff, but most of them is common sense. So what we want to do is we need our examples. This is supervised learning. So we have here 7 lines in. We have a lag. We have like a history memory of the total power consumption. And we have a FOST. So from this line, we should be able to predict the total. And when we do machine learning, we build a model, a mathematical function that from the input variables can explain this, predict this. And then you build some kind of model of that. In this case, you have a model of an artificial neural network. And when this is built, it's actually trained and built, constructed by tuning a lot of different ways in this network. And you just tweak them in different ways, in a smart way. And then you see, okay, I tweaked it a little bit. Let's see how good it fits the data. Oh, it was a lot of errors. I did a lot of errors there. Okay, change the weight that affected that output. So we'll get a smaller error for those. And then you try it again. So you have a faucet, and then you just optimize the network iteratively until you get as low error as you can. And when you can do that, then you can forget about this data, and use it to predict new data where you don't have the target variable. That's machine learning in a nutshell. Yes?
I think I missed the problem statement. But you're saying you want to, from a small section of the network, want to predict the consumption of the whole power grid.
Okay, yeah.
Otherwise, you're not predicting.
I missed one thing. Yeah, what you want to do is 1 hour ahead of time, say how much will this 7 household consume. And you want to do that because if you know that, then you can balance the load a little bit by starting the heating in different intervals, something like that.
Right.
So 1 hour ahead. Okay, great. Thank you for that. Feel free to give me corrections and input as we go along. So we build a model to be good at predicting new instances from examples that we have. And then when we have that, we can do the predictions. So this is a case of predictive modeling, batch training. I will give you an example later. And so it's a task of building a model from available data that can be used to make prediction on new data. One thing that is important to realize is that training the model, I mean, the typical setting is you have your device that you collect data from. Then you need to build this knowledge base of examples, your faucet. And then you have a model that you tune to minimize the error according to some score function. And this part is the computational expensive thing, to train it. When you have it and it's ready, you can do predictions straight away. You take the data straight to the model and you can do prediction, and that's fast. So one way to speed up machine learning is to train it in the cloud and then just use the model. They will be fast later. I will come back to that. So machine learning in an IoT setting is typical. In this case, we should have some kind of picture of an oil pump that today can have over 100 sensors monitoring them. The data is streamed to the cloud. The analytics is done in the cloud, and depending on the outcome, we can predict some kind of failure or some state of degradation of this machine. So this is a typical way that we do it today. But this approach comes with all these hurdles we were speaking about before. This is actually, if you don't have a good internet connection, if you have a really high frequency reading of your data, you will get all these problems. You won't be able to capture data, you won't be able to send everything to the cloud. You won't be able to do it in real time because you first need to send the data to the cloud, analyze it, and then send it back, maybe. So you will lose, you will get all these challenges to do it. So what's the alternative then? Well, ABI research claims that AI will be extending or going away from, or let's say extending now, from the cloud-centric approach to edge computing. That is, the AI will be embedded in the devices. It won't be doing it in the cloud. It will be doing it straight on the device, straight on the cell phone or straight on the oil pump. Why send it up? If you have sensor, you will still have some kind of processor out there. It's better to do it there. And by 2020, they said there will be 2.7 billion active enabled devices and actually doing the learning on the device. So this field is called edge analytics, and that's where we claim that the future of IoT will go. It won't totally replace cloud analytics. It will still be there, but it will be a complement. And what will be a complement for? Well, we can analyze real-time data without while reducing the network traffic. Imagine when you have 50 billion devices and everyone wants to send the data to the cloud. It won't happen. It will be congestion there. So we need to do it in a smarter way. And doing the AI actually out here on the devices will help us with that. We can use all the data and actually getting the results in real time. The alternative is to just sending hourly averages to the cloud and analyzing that there. But then we will lose so much information. We will reduce the latency in the round trip here, so we don't need to wait. And we don't need to transfer all the data. Some data may be sensitive, so we can actually handle it on the device or on premise. We don't need to send it to the cloud. It can be done there. And we'll be less dependent on internet connection as well. And of course, if we have some kind of processor power out there, we will use that as well. So there's a lot of advantages of actually doing the learning on the edge device. When we're speaking about edge device, the question comes, what is an edge device? What kind of equipment is it? Well, sometimes you speak about different tiers. You have the gateway tiers, for example, an ARM A7, the gateway tier to the right there. There you will have more memory than you need. And it's also at the industrial tier. Sometimes the gateways is referred to as fog. And then when you come to smaller devices, it's edge. But now it's not clear exactly. But we can call everything edge, at least today. But the important thing is here that the lower we go, the less, especially memory and CPU power we get. So from 64 megabytes or as much that we need down to 1 megabyte or a few Ks. And this is not a typical case for machine learning. As a researcher, you often look at, I want the most accurate model. But that doesn't mean that just because I can predict the weather good in tomorrow, it won't be able to run here. Because I need to, when I'm doing edge computing and edge analytics, I need to consider the constraints that we have on edge devices. How much memory do I use? How much CPU do we use? So it's a different field, and you need to look at it in a structured way and adapt the algorithms to get the most of it and to be able to do edge analytics. And typically, you will have limited CPU, limited RAM, and limited storage. It will be hard to store all the data that you need to actually learn the model. And IoT devices ranges from so many tasks. So how can you design something that is so versatile that it works for the lawnmower, bicycle, airplane, or wherever you have a device there? You need to have a thought about that, which kind of techniques that you use. And maybe more typical for IoT, that is, you won't really know where the device will be running. The environment of the device is often unknown, and it can change. If you have a mobile device, let's take a truck, it will behave differently if it runs in Kiruna or in Brazil, or just in Kiruna and Malmö, depending on the temperature and everything. So we think that models needs to be tailored to each device. The typical way that you do machine learning today in the cloud is that you take data from a fleet of vehicles, analyze it, and then use it to predict something for each truck. But then you get some kind of average that won't tell you so much. What's normal for one truck driving in Brazil will definitely not be normal for the one driving in Kiruna. So instead, we should do one model in each device, because then we can learn what's normal for this one. Even when you ship a machine to a new plant, it's specified for one range of operation. But then you will put it in a different setting, and that setting may be different, and it can change over time depending on what happens in the plant. The typical edge analytic architectural overview, then, how does that look? Well, you will start with that you have your machine here that you want to maybe perform predictive maintenance on. To do that, you need your sensors, and you need some data extraction layer. That's the first part. And now we know that to do machine learning, we need to have a knowledge base, a set of examples that will represent the normal behavior or something like that. So we need to stream that up to the cloud or to some storage point somewhere. So we can save that. create a model, tune the model, so we can learn something, we can actually explain what's happening. And then when we have done that, we can send the model to the device. Then we have a model that can explain a very dynamical and complex behavior. And when we have the model on the device, we can send the data straight to the model and get an instant feedback to some kind of controlling system. And that control system, of course, must tell the machine what to do. Shut down because you're going to have a failure, or increase torque to get a better product, or separation, or whatever. Yeah? So that's a typical edge analytic overview. And then the idea is that you will have one model for each machine. Each machine will function differently often. And I've been speaking about this just before. A problem for IoT devices is that you have a changing environment, and it can create problems in many different ways. You have seasonal related factors, for example, that the temperature affect the process. If you have a separating sludge, some physical product from the water, that will be dependent on temperature. And if you want to predict that, you need to start collecting data for a year, 2 years, to be able to, because you learn from examples. If you haven't seen how the machine works in the summer, you can't predict it. So then you need to collect data for that, and that will take a long time of learning that. So that's something that you need to think about and handle in some way. The device itself may change. What happens if you change the transmission in the truck? It will behave differently. So how can we relearn or adapt the model to changing behaviors? And of course, IoT devices are often mobile and operate in different environments. And finally, machine often optimized for worst case scenario, not how they will actually be used in the plant. And that may be result in suboptimal performance. And the point here is that you don't know how it will be used. So the best thing is if you can learn from the device where it is, you can tune it, adapt it to the site where it's actually going to be used. So this is hurdles that needs to be tackled if you're doing this on the edge. Our substation here, again, predicting the total consumption 1 hour ahead. We have two very nice diagrams here with nice color-coded. I will explain what it is. The blue line is the real, actually the target variable. The orange is the predicted. The red one here, and you read that on the first y-axis. The red one is the outside temperature. You can read it here. So for the training data, the top chart, you can see that the temperature almost never rises above 15 degrees. But we can see that the model has learned really good the pattern here. Then we apply it. Then we say, okay, let's put it on the edge device and run it there. And of course, then we put it in spring. And then we see, here we have 15 degrees again, that we start to see temperature above what we've been training on, here and here and here. And we see that straight away that the errors start to appear. We can't explain this part. So the models that you create with machine learning is never better than the data that you give it. It must be representative. So if you want to learn this with batch learning, you need to have data for a year, at least 2 years. And that's quite boring. We want to start right now. and maybe we also, it can be other changes, so we want it to adapt the whole time. No one wants to wait a year. That's just boring, no? So, what can we do? Well, there's one field of machine learning that's called online learning. That is, instead of having a training set, the typical setup, where you optimize the model on, you optimize the model continuously. You never stop training it. So that's called online training. And then you get an adaptive model. A model will always adapt to its environment. And another advantage of that is that the computations are distributed over time. Instead of calculating 100,000 examples and trying to minimize the error over that 1,000 times, there will be a bottleneck of computation. You will do each time one new example arrives, you will tweak your model a little bit. And then you can do that on a small processor without overloading it. Just tweak it a little bit, and the model will slowly adapt to its environment. You don't need to store the data because the model itself will be representing the data. So you will lose that hurdle. And you don't need so much data either. You don't need to wait a year because you will adapt as your environment changes. You will be a little bit slower to learn in the beginning, but it will catch up and you will get a better fit to the data. One question you can think about it on the negative side is how fast should the model adapt? Well, if you want to have a really accurate model, you should have a fast adaptation rate, but then if the machine starts to deteriorate, it will learn that and say that that's normal. On the other hand, if you do it slowly, you will see that it starts to deviate. So it depends on what you want to do. You want an accurate prediction, or you want to be able to say something is going wrong. And the advantage of online learning as well is that the architecture overview is much more simpler. Here, you don't need to send the data to the cloud to learn again. You can just send it to your algorithm. It's so advanced you can't almost see it here. It's just matching. It has a cloaking ability as well, online learning. So you send it straight to the model, adapt it, and it can give you feedback straight away. So you don't need to send all the data to the cloud. You won't be so dependent on the good internet connection or the bandwidth or something like that, because you will be on the device.
Question.
Yeah.
Are we going to talk about here that moving computer powers down into the local environment? Are the algorithms the same that you run in cloud and that you run in the local environment?
Yeah, some algorithms are the same. Some are not suited for that because they either are computing. I mean, take deep learning, for example. It takes so long time training. So it will take a long time until we see adaptive deep learning on a device. But you can have, as I said before, the training is expensive, but the model can run. But it's still, deep learning is still tough. So they're doing special chips now to speed that up. So that's why you see. But yeah, basically it's the same. Maybe it's a subset of the one that you use in the cloud. But the one you can use on the device, you can use in the cloud as well. Okay. Let's see, something else. Fast execution, adaptation, and much more suitable for the edge devices. It's simpler, and simpler is often better, no? The same problem with online learning. You can see that just in the beginning here, we're way off because we haven't learned anything yet. But then we'll get good straight away, and you continue. And even when we see stuff we haven't seen before, it adapts. And then, of course, the difference is here that we don't stop the learning here. We continue the learning the whole time here, so we adapt. And that's also a good thing because another way, you don't need to start from scratch. You can actually send a model that is trained for the whole fleet. This is a general model for my oil pump. They generally work like this. And then you can continue to adapt it for its special cases. And then you don't need to have a startup with slow learning. So it's quite nice. And of course, what happens in the beginning then? Well, in the beginning, it will be a simple prediction that will be like a moving average. And then the prediction will, or the model will grow in complexity and making more advanced predictions as it goes along. That's how it basically works. If you have a little data, well, just guess the average. But when you have more data, you can start learning and explaining more things and making more advanced predictions. So that takes us to potential challenges. No, we've been there. Typical use cases. I'll have a little bit to drink here. What can we do? Now we know about the huge potential of IoT and what machine learning is and what we can do with it. Now we'll see some typical use cases and how we apply it in reality. The first one, of course, is predictive maintenance. How can we decrease unplanned downtime or estimate when a service interval is needed on an individual basis, not on a statistical model that is for to be 90% correct that this one is not breaks based on all the other machines I've been seeing. Yeah, we should service with each 3 months. No, something depending on how it's been running, how we'll do that. Well, you have three ways to go about it. First, it's supervised prediction of failures. If you have a fleet, or if you have many devices and they break constantly or they often break, then you collect the data from each failure. Remember, you need to have example of the thing that you model. Collect the data from the failures and when the machine is running properly, and then you train a model on that. So it can just, then it will predict it will be likely to fail in 10 minutes. But then you need a representative set of failures, and it's not 10 or 50, maybe it's 100, 1,000 cases. If you have that, this is the way to go, because then you can also get what is wrong, what is going to happen. So this is the most powerful, but it's also the most requiring data from your fleet. The other one that you can do straight away, or the simplest to start with, is a deviation from normal behavior. Then you train a model to model the behavior of a well-functioning product. This is how it behaves the first month when I've been running it and running the process cycle 3 times. Then I learn that. Then I can have that as a reference model and see how the performance deteriorates. And I mean, this is not like the output won't be 50%. I mean, it will be depending on the condition, how it's run, how should it react in exactly these circumstances. I will show you an example on the next slide. It's a movie, so just keep with me for 5 more seconds and then you will get something really exciting. It will be worms chasing each other. Right. Last approach, anomaly detection. Here, the difference here is that in this case you need a target variable, something that can signal the performance of the machine. It can be the temperature in the gearbox, it can be vibration, if it's something that is related to the performance. You need that to do the normal behavior. In this case, you say, well, we don't have anything like that. We just want to look at the data and see when we get an example that doesn't fit in. And you can do that, but the problem with that in an IoT setting is you will just say, okay, here we have this instance, the model, the machine appeared in a way we haven't seen before. And then you need to have an engineer look at that and explain it. And that's not really feasible if you have 50 billion devices that need monitoring. So this is a better way to go about it if you want to do it automatically. You can learn more things about it if you have the time. So here we have an actual example on a decanter separating sludge from water or something somewhere. What we're predicting here when the worms start crawling is the actually bearing temperature over here. And the blue chart here is the actual temperature. The green is the predicted for the normal state. This curve here is the recommended maximum temperature. And here we get some kind of score about how it deviates from the normal state. And what's interesting to see here that in this case here, the actual temperature is up here. It's still below the maximum operating system. So a threshold alarm wouldn't go off. But the model says that, well, you should be over here for this particular settings. You shouldn't have a higher temperature here. Something is wrong. And you can also see that after that, they stop the machine, grease it, and then start it again, and it's off. So that's one way how you can see it. You wouldn't see it with just looking at the curve, but looking at the reference model, you can see that it deviates here. Another way to use predictive modeling is to, if you predict it 1 minute, 5 minutes ahead, you can see that, well, in 5 minutes, you will reach maximum temperature. If you continue like schedule, well, then of course you can tweak the parameter settings to reduce the torque or something to not go there and get a more optimized process. And on that subject, of course, predictive control is a really old, not really old, but it's in the IoT era, it's 20, 30-year-old field, engineering field of how do you optimize the control of the machine. And in those cases, you can also use a predictive model. So what predictive control is about optimizing the parameter settings for a system that is dynamic and have some kind of inherent inertia. That is, you won't reach the target performance in one time unit. For example, if you want to heat this house, heat this room, you can't do that in 1 minute. You need to do it in maybe 2 hours time, depending on the outside temperature and everything. So if you want to control the ventilation, you should have some curve deciding that, okay, for the next 5 minutes, use the temperature of this, and then you increase it, and so on, depending on, we have a weather forecast saying coming up here, there will be, the sun will be out, so you don't need to heat it so much, and so on. So, and then it says that in 5 time steps, you will reach your target value. And so predictive control is about optimizing this control sequence. And it works that first you train a predictive model that can predict the outcome X steps ahead of time. Given a control sequence, what will the output be? If you have that, and that's a predictive modeling, and then it's old-fashioned, old-school predictive control on top of that. So using that model, you use some optimization framework to calculate an optimal schedule for your machine to reach that level. You execute the first step, because the idea is that you have factors that you can't control. So then you execute one step and see, okay, what happens now? What does my machine and my predictive model say now that the temperature will be for the new settings, and so on. So that's another way that you can do it. And then, of course, you have descriptive modeling. It's based on the thought that if you can predict something accurately, following the temperature in a gearbox or something like that, that model has learned how the device works. And if it has done that, it can be used to explain how it works. So you can see which of the variables that is important for this machine, for this truck. Why is it not working as good as it should up in Kiruna? Or why is it not working as good as it should right now? So one example could be that based on data from 6 months, explain how the usage pattern of a gas turbine engine has influenced the degradation of the engine. So we have the engine, we have collected data from it for 6 months. We built a model that can explain the degradation somehow. And then the model says that the main contribution, the main influencing factor is actually the compressor outlet air pressure. Of all these factors, that's the main influencer over the whole lifetime of that. But it can be more interesting to look at a certain state. Here we have a well-functional engine, and you have the importance for describing that engine. You can see here with the different bars, and you can compare that with an engine that has been degraded 25%. And when you compare it, you can see that, well, the thing that differs the most is actually the turbine exit temperature. So you get some, I don't know anything about gas turbine engines, but the model can explain the degradation level. So if we believe that is true, then this also should be true. And then this, of course, should be verified by an engineer or expert, something like that. But this is a typical way you can go about doing root cause analysis. If you have a machine that failed, you can look at why or what signifies this machine. Another way to do it is that if you have a fleet of vessels having these kind of engines, you can see that, well, this one over here has this pattern, this has this one. You can probably optimize the engines comparing how they work in different settings. So, some conclusions then. First, we saw that IoT have a huge potential, and to unlock it, we need to overcome some big hurdles. And if you should pick a few, the first one is interoperability. That is, the IoT devices need to be able to speak with each other. Otherwise, we can lose as much as 40% of the potential benefits. So it's important that the devices can speak with each other, that you have a strategy for collecting all the data in one place, or that you work with some really good integrator that can help you with that part. In that. Security, there will be many more opportunities for potential breaches. So you need to have a strategy for handling that. And then you have the intellectual property. Who owns the data and how can you send it to different places, to different plants? And in the soon future, we will have so many devices that if we send everything to the cloud the whole time, we'll just flood the network. So it's not a reasonable approach. We need to do something differently. And one way, of course, is doing edge analytics. And most data is not used. So we need to use it in a better way. And how do we do that? Well, AI will be moving to the edge. It will be a crucial complement to cloud analytics. Cloud analytics won't go away, but to really reach the true potential, we need to do more thing on the devices, and we need to do it individually for them. So we need to do edge analytics. And we need to use, if we do that, we can use all the data in real time and making real-time decisions. It will be at the source straight away. And if we do that, we don't need to send the raw data to the cloud. So you will use the bandwidth better. You only need to send the relevant KPIs or send data when something has gone wrong, or saying that now this machine is running abnormal. Give me the last 10 minutes of data so we can look at it more closely. We will have an increased security since we won't be sending all the data. We don't need to. If the internet connection goes down, we can still learn and surveil and control the device. And we'll be less dependent on internet connection as well, of course. And to do this in a setting with devices that change place, as changing the environment. We should have one model for each device, and we should do it with online learning. That's the most suitable for IoT settings, is my thought. And that's actually more or less what I was planning to tell you. I can finish with, I didn't say what Ekkono was doing, because if I would have done that in the beginning, I would have had all this talk explaining what we do. Because what Ekkono is doing is we're trying to take IoT devices from connected to smart. So we're doing an embedded library for edge analytics for the Internet of Things. So it's a small software that you embed in your own code. So it's not a platform, it's not Azure, it's not Amazon Web Service, anything. You can run it in Amazon Web Service, you can run it in Azure if you want to. It's just a machine learning library that is optimized for doing edge computing. It has online learning. You can train them all on the device, one for each one. So we're a software library that you embed. We don't do anything else. If you want to have it in there, we should speak with one of our partners. Really one good there, I think. There and there. It's designed to be resource efficient and have a small footprint. And it's designed for programmers. The idea is that data scientist, I read, was the sexiest professions in the year 2020. It's we're really hot. if I can say it myself. No, but there are not so many data scientists out there, so it's hard to they're hard to find. So we try to design an API that will do a lot of the data science for you. It should be easy to get going, because we don't want to sell something that is not used. You should be able to use it and get efficient, smart devices in land. And of course, then it's as well designed to be simple to deploy on the devices. So if you want to speak with us about that later, we will be around here, me and Anders, my colleague, definitely, and Bengt as well. And with that, I will actually leave over to questions. I hope we will have a really interesting discussion on this topic. Start with a question from the crowd.
Yeah, it's always fun to find a problem when someone is presenting something. No, but I just want to discuss. I think you have an error in your prediction on why it will go to the edge.
Yeah.
And I don't really think it's a bandwidth issue of the data from so many devices. It's actually the fact that many companies are now going or have gone to the cloud with their data centers. So they go from on-premise data center to the cloud, and now you get a bill for how much you're using your computers. So it's actually driving cost in the cloud. Your compute utilization and your memory and your storage utilization now has a number.
It has a cost, yeah.
But that's just my personal.
Yeah, I mean, yeah. It's at least, if nothing else, it's another reason.
Yeah, you can say it's another reason.
Because
we can engineer the networks, but it has a cost.
Yeah, and the question is if we want to pay it.
Yeah, which we start to see. You might not want to execute everything in the cloud.
No.
So I think it's a very good motivation for going to the edge.
Yeah, definitely.
And latency, of course.
Yeah, the latency.
And the data, blah blah blah.
Yeah. Yeah, so it's definitely.
Because you can look at it's not anything to do with artificial intelligence, but you look at the IKEA connected light bulbs with a gateway. It's actually doing a lot of things in the gateway itself for a couple of reasons.
Yeah. Oh, that's true.
Question? Well, I mean, one problem with going to the edge would then be that each individual component won't be able to see the other device's data. I mean, so one major benefit with having it in the cloud is that you can get an overview, you can get all the data, and maybe find a better decision based on all the data. You mentioned it. You don't foresee that this is a big thing, a big advantage with doing it in cloud.
No, but it's. I mean, that's why we're saying it. It won't replace cloud analytics. It will be a complement, because you can do there's definitely use cases where you learn from the fleet, and I said you learn from everything, and then you can adapt it in the device. And then in some cases that you won't be able to send it to the cloud. So it's another tool for doing the analytics. So definitely, it will still be important to doing stuff in the cloud and looking at the big picture and all the things you can learn. One thing there and another thing down in the edge.
But it's sort of a layered approach where you have some relevant KPIs going into the cloud, and then there you can do that analytics. But you can't send all of the data, so it's good to have that layered approach. I think that's what we're saying with the edge part.
Yeah,
I think what you have been describing to us here is really system identification and a smarter control system. AI, to me, is something totally different. AI is another level of intelligence where you do some lateral thinking, taking in, but there's so many sensors in different aspects that you can really see unexpected influences on your process. But by taking it locally, you would never see those because you don't have that lateral network that really sort of picks up all these seemingly unrelated factors that actually could be the reason for your problem. So this is not AI. This is a little bit smarter system identification and control.
I wouldn't say that because, I mean, again, I call it old-fashioned machine learning. Machine learning is part of it. Depends on what you put in the artificial intelligence. And I don't agree that you won't find something unexpected, because we have cases that with just 4 input variables, pressure, temperature, and flow, they learn something they didn't know before. Oh, is that true? Because you will see patterns and stuff that you can analyze. But of course, you're speaking about the more general AI, and of course, again, if you connect more sensors to it, you can learn more and getting more new things. Definitely, you can do it in that. And I mean, that's the main thing. The difference between statistics and artificial intelligence, machine learning, is actually, well, they intertwine. But if you wanted to have one line in statistics, you test one hypothesis, something that you believe, and see how much the data support it. While in machine learning, you try a set of hypotheses and see which one fits the data the best. So then you may learn stuff that you didn't know from before. So of course, going locally, going to the edge, you will limit the available sensors, but I promise you will learn new stuff.
I just want to add that you can classify it like some kind of data scaling actually on the sensor level.
Yeah.
This online learning, how do you avoid that it derives too much or that it goes in the wrong direction?
Yeah, I mean, the main parameter that you have to tune there is the adaptation rate. How fast should it adapt? So it doesn't, and again, it depends on what you want to achieve. If you want to have a model that describes the normal state and then see how much it deviates, then you should have a slow adaptation rate. It's hard to set exactly number, so you need to tweak that for each application. If you want to have an accurate model that just explains it 1 minute, 2 minutes ahead, then you should have a fast adaptation rate. But that's what you tweak is how much because the model will always forget stuff. That's how you tweak it and make it. You don't let it retain the whole memory. So while the learning goes on, you will throw away memories, so to speak, and then add new ones. So then you will have a better understanding, and you won't throw away memories randomly either. You will, since you have your faucet, you have your knowledge base, you will look at how good are my memories and throw away the bad ones and keep the good ones and let them become even better. So that's how you tweak it. But it's not a silver bullet. It won't solve all your problems, but it's well suited for IoT use case, I would say. So the basic answer is the adaptation rate is your main parameter to tweak, and then it needs to be tweaked for the use case that you're in. Yeah.
You didn't mention about the algorithm that you're using in your API. I mean, is virtual machines, integrators, MLP, which one are you using?
Yeah. Yeah. Good question. In Ekkono, we have selected a small subset of all machine learning techniques, and we've done it in a way that, because normally you want to, like I said, optimize the accuracy. Only you want a pretty model, accurate model, but we want to be able to have a model that is not only accurate but also have a small memory footprint and low CPU cost. So we have a range from simple models, multiple linear regression, regression tree, model trees, random forest, neural networks, and support vector machine can be one candidate to take in later. But we want to have a range, so you can go from a powerful memory consuming model to a small simple one. Because in the end, the problem, a random forest is only better than a linear regression if the problem that your model is non-linear and you have a lot of data. If you have a linear relationship, multiple linear regression will be as good as a random forest. So why not use the simplest technique for that? And that's what we optimize for you. So we try different models and see how good can we become, and then reduce the memory cost without losing accuracy. So it's a trade-off there. So the answer to your question is that we have a range of algorithms that we choose from.
You try to optimize your algorithm for your hardware constraint that you would have, or you choose the algorithm based on the hardware constraint you would have?
Yeah.
Story that you have different, you're using different algorithms, or you optimize the algorithm for that platform that you're going to use?
We do it in two approaches. First, you can give constraints on how much memory it can handle, or it should consume. So we can choose first an algorithm that is best suited for your constraints, and then you optimize that algorithm for as well. Like in random forest, you can, if you add trees to random forest, you will always be more accurate, or at least it won't hurt the performance. As more that you add, you will reach maximum accuracy, and then it will just level off. You won't gain anything. So one thing that we do is looking at the gain chart of the accuracy and stopping it when you don't gain anything more. So that's why one example of how we can optimize the algorithm, and then we can optimize which algorithm that we use as well by looking at the big pictures. So we do macro tuning and micro tuning.
And how are the overfitting things? Have you faced any problem with overfitting with your customers?
Well, again, it's overfitting is always a danger. Random forest is a good technique because it tends to not overfit data. More trees will, as I said, not. It won't increase the accuracy, but it won't overfit either. So we have standards, typical approaches of evaluating the models. Tenfold cross-validation is not so good for the IoT setting because you have a time series and you want to cheat. So we're using a holdout and backwards fitting. So we have schemes for evaluating the fitting and reducing the amount of overfitting as well. That's a good question. But in general, random forest is one of my favorite algorithms because you have so many advantages, except that it uses more memory. You have very few parameters to tune, and you don't have a big risk for overfitting and so on. So if I should just go with something, I would start with that, and then we have something to compare to as well. That's a benchmark.
A question related to the example you were using with the power consumption estimation.
Yeah.
I was wondering how you're handling. You could say I have data to train the model for a partial year, and then you would know there are certain aspects that will have a great impact. Let's say you can say probably a lot of the users have electric heating, so that will impact the scale of things.
Yeah.
But your model didn't have data to train the model of that. So are you including that in your because you also have a predictor quality metric, I think.
Mm-hmm.
So you could warn like the consumer of that prediction. You could warn them that now my predictions are pretty bad.
Yeah, yeah.
You could kind of have a second layer where you will know my model is.
Yeah.
To fail.
Yeah, definitely. We're also working with a framework is called conformal prediction, and that's a machine learning framework for estimating or for making predictions with confidence that you want to have 90-95% confidence that you're correct. And the nice thing with that, when you compare it to confidence intervals, which is based on that the errors are normally distributed, which is never the case in machine learning, and that you get the same intervals for all the values. Conformal prediction will give you, it's not based on what kind of distribution it is, and you can normalize it so you will get harder, simpler prediction will get a smaller interval, and a large one will get a big one. So we're working on that as well. So you can always have an estimation of your accuracy or getting an interval instead of a point prediction. And of course, you can have an online evaluation of the accuracy right now as well, that you can see. So definitely, so you can take that into account.
If I understand it correctly, because I'm not an expert in this field, you are selling a software package. You said you could buy it and you could adopt it, but that package then needs to have a lot of different input parameters that you set up here, and you give examples, you get questions here, and you respond to the questions there. But do you have a full overhead description of how this software is working, and if I'm going to buy it, what parameters can I adjust, and what method can I apply to my specific task?
Yeah. If you want that, I can. We will be happy to speak with you for many hours. I didn't want to have a cell meeting here. I wanted to give you a broad talk about IoT and where we think we're going, and just to raise those questions. So we'll be definitely going to that. But we can say it like this: to do machine learning, the thing that is general is the algorithms and how you tweak them and apply it. We do that, but 80% of the accuracy of a machine learning model is depending on the data you put into it. And I'm not an expert in gas turbine engine. I'm not an expert in substation and power consumption. I'm not just a computer nerd. So that's why we don't do that part. We want to have a tool that can give engineers with a good understanding of the machines and the things they model, a tool to model and work with machine learning. So what you, as a user of Ekkono, do is to define what kind of data that should go in. Then you will get help with tuning and building the model and getting an accurate prediction and be able to run that on a small device. That's what we do. And we do it in a layered process as well, so that if you're a novice data scientist, if you don't know so much, we can automate most of the things. We can do reasonable, good tweaking of the algorithms and the techniques. We'll do that based on the data. So we'll find something that will work really good for you. But if you're an expert and you want to have everything at your fingertips, you will be able to do that as well. So you can tune everything that you could do in some open source like scikit-learn and something like that. You will have the same options, but you will also have an simplified, automated API as well. Yeah.
Question about how interoperable are models from different kind of tools in general? So say that I have available to me data that I also want to train in the cloud, and I want to use your software. Is there ways to sort of benefit from that trained model in your code and vice versa? Or is it that is it either or? If you run your software on the edge, you don't really benefit from any cloud.
Yeah, I mean it's an interesting It's an interesting question because it relates to some research I've been doing with Oracle coaching. I can have a special session we do about that, but that's how you can use one model to train another model, and you can actually gain accuracy by using another model as a filter of the input signal. So there is way. There's not into our system right now, but just basically, and it's a really smart idea that you have there. We can speak more about it. The other way is that, I mean, what you put into the system is the data. So you can as well feed the cloud and the device with the same data and do different stuff. Do different one model that explain the whole model for the fleet and one for the individual. And then in general, combining models is always a good thing. It's called ensembles, and an ensemble of models is more robust and giving you better prediction than a single model. So it's a good idea. Did you have a question behind that? No? Oh, okay.
So follow-up question.
Yeah.
So say that you have this idea that I don't know if the original is just fitting for my domain best, but would you think that I think I answered the question myself, but
that's the best questions. I love them.
That depends on the domain, obviously, but the thing that you train the exact same sensors, the exact same turbines or rooms or what have you that you monitor. Do you think that those models will be very different, or will they be very similar?
Yeah, I mean, it depends. I mean, if they're running in the same environment, they will be very very similar. And if they run in the same way, if you have two twins standing next to each other, running the same process, then they will be very similar. And the good thing with that is that we're having techniques for algorithms for change detection to observe when one machine is changing. But of course, then you need a machine that is functioning normal, and then you need to train data with that. But if you have two twins standing next to each other, you can compare them and say, now this one is starting to behave differently from that one. And then you don't need to have a machine learning model. You can have the machine, you can have a physical twin and just doing change detection from the data coming constantly from them if you're running the same process. So it's a way of using physical devices as algorithms as well. I don't know if you know, have you heard about Mechanical Turk? Yeah, right now it's a service on Amazon, but from the beginning, Mechanical Turk was a chess game in the 18th century, an automated chess game that they travel around with in Europe, and this automated chess game beat several of the big champions. So there was a big thing. But the thing was, there was a small guy sitting underneath pulling the levers, and and so it was probably from Turkey. That's why it was called the Mechanical Turk. And now Mechanical Turk is a service on Amazon, so you can buy or you put out small tasks that humans are really good at solving. For example, image recognition. What's on this image, or what does it say here? And then you pay them a little bit. And the nice thing is, then you combine them with machine learning techniques, with ensemble techniques. So then the people are the algorithms. It's really smart and cool thing. And that's it was just something I got from comparing to two machines and then to from that. Yeah, machine learning is cool. More questions?
I mean, from this question more from the business perspective. So there are many countries that you have in the market. I mean, not in Sweden, but in the whole Europe. Do you have any pattern which makes you unique in the business?
Two ways to answer that question. First, we don't have so many competitors working on the edge. There are some, but we haven't seen anyone else doing online learning on the edge right now. maybe out there, but so far we haven't seen it. And according to patent, what do you call it in English? Patents, yeah. No, we don't have anything. So because our approach is that we want to facilitate that our customer can create patents on the knowledge that they find with our techniques. So we're not constraining our knowledge with patents at the moment. So we think that the solution will be so good, simplify so many parts that our customer wants to use it, and it will be hard for someone to copy it exactly as we've been doing it. That's the approach right now. We'll see. So we don't have our own algorithm that is better than anything else. We have a combination and the know-how how we do it. What we have is a combination of 12 years of machine learning research and 10 years of optimizing cell phone traffic in the networks combined. So we have expertise in optimizing implementation and doing throughput of data, and we have expertise in machine learning. So that's the strength of Ekkono, combining those two together. And I know, at least as a researcher, I thought I was a good programmer before, but I learned that no, I can do the machine learning part. Really good questions. I love to have this many questions after. I will just see if we have something from our audience. Someone still with us? Let me see. Oh, we have grown. Let's look at the chat. If anyone out there still with us that have a question, you can write it in the chat window, and I will see if I can answer it. We'll give you a few minutes to do that while we see if we have some more questions.
Will you make the slides available?
Yeah, I think so. We will come back to you on that. Yeah. Everyone out there in the webinar, everyone is looking at you right now, waiting for the question. Yeah. But no. Okay. Yeah. So I think we will have some mingle and some talk here. Some of the work. Me, Anders, and Bengt will be happy to answer questions about Ekkono more. If you have some question you didn't want to ask here in front of everyone, and Anders will love to tell you more about the business model and the pricing stuff.
You got the red question mark then.
Or maybe there's someone active.
A red question mark?
Yeah, there's a question mark at the bottom of the panel.
Am I blind? Up.
Small menu.
Ah, okay. Oh, there. Click to open question pane. Ah, how long has it taken to develop the technology? From Anthony. Well, the technology is based on the last 7 years of my research, so it's on the findings I'm doing that. So, and we started with my research produced code, and now we ported that to C++ because we're having the API is written in C++ 14. You can code in Python. We have bindings to Python, C#, and Java. So you can actually develop models in Python and then run them on compiled code on the device using C++. So the model representation is language independent. So so that porting to that has been going on from we're a startup. We started in was it February last year, more or less. So that's the time it's been taking us to re-implement it in an effective and production quality level. Great. So, thank you. Yeah, real time. Sorry then, Anthony, that you can't be on the after work starting here now, but we will have you in our thoughts. Okay. No more questions? Okay. Thank you very much.
Thank you.
Stop recording.